Now in this lecture I will answer two questions. In the first question we find out the perimeter of this quadrilateral ABCD, and in the second question we find out the area of this green shape. So we'll start with the first question. In the drawing we have quadrilateral ABCD. This is line segment BQ, that equals to 10 units in its length. This is line segment QC, that equals to 40 units in its length. This is line segment QP, that equals to 20 units in its length. In addition, we know that line segment AP equals to line segment PD in its length. So if we define the length of line segment AP as x, then the length of line segment PD must be also equal to x, because they are equal to each other in their lengths according to what is given as the question. Again, our task is to find out the perimeter of this quadrilateral ABCD. The perimeter of any quadrilateral is equal to the sum of its four side lengths. That is to say, in this case, it is equal to AB plus AD plus DC plus CB. So, in the first step, we will do a construction. That is to say, we will draw perpendicular on AD at point P. Again, we will draw perpendicular on side AD at point P. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. In the next step, we will extend the perpendicular from point P until it touches side BC of this quadrilateral ABCD. And we define the touching point of the extended perpendicular from point P and BC. This point is point M. So here we can implement rule 18 in our drawing. So repeat quickly on rule 18. According to rule 18, if the sum of two one-sided interrogants is equal to 180 degrees, then they lie between parallel lines. In the drawing we have line A, line B, and this is line C that cuts the two other lines A and B, those 2 points. Those two angles, alpha and beta, they are both defined as one-sided interrogants. And according to this rule 18, if the sum of those two one-sided interrogants is equal to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then those two one-sided interrogants must be located between parallel lines. That is to say, line A is parallel to line B. So whenever you have two one-sided interrogants that the sum of them is equal to 180 degrees, then the two one-sided interrogants must be located between parallel lines according to this rule 18. So we can actually implement rule 18 in our drawing. One, because in our drawing, those two right angles, they are both defined as one-sided interangles. And the sum of those two right angles is of course 180 degrees. And therefore, according to rule 18, those two one-sided interangles are located between parallel lines. That is to say, line AB is parallel to line PM, according to rule 18. So, I write it down, and we found out that AB is parallel to PM, according to rule 18, of course. Likewise, the sum of those two one-sided interangles is equal to 180 degrees, and according to rule 18, therefore according to rule 18, those two one-sided interangles are located between parallel lines. That is to say, PM is parallel to DC. So PM is parallel to side DC according to the same rule 18. Likewise, the sum of those two one-sided interangles is also equal to 180 degrees, and therefore those two one-sided interangles must be located between parallel lines. That is to say, AB is parallel to DC. Again, according to rule 18, AB is parallel to DC. So in total, we found out that all those three line segments AB, PM, and DC, they are parallel to each other. according to rule 18, of course. This is side AED that connects the three parallels together, and this is side BC that also connects the three parallels together. According to the basic proportionality theorem, according to the basic proportionality theorem, a special relationship exists between AD and BC that connects the three parallels together. The relationship is as follows. AP over PD equals to BM over MC. Again, according to the basic proportionality theorem, a special relationship exists between AD and BC that connects the three parallels together. The relationship is as follows. AP over PD equals to BM over MC. So, I'll write it down. According to the basic proportionality theorem, a special relationship exists between AD and BC that connects those three parallels together. The relationship is as follows. AP over PD equals to BM over MC. And again, according to the basic proportionality theorem, AP over PD equals to BM over MC. AP is X, PD is X, and therefore AP over PD is X over X. So X over X equals to BM over MC. X over X is of course 1, so 1 equals to BM over MC. Here we multiply this equation by MC, and finally get that MC equals to BM. And MC equals to BM. Or BM equals to MC. This is line 7 BM, this equals to line 7 MC. That is to say, point M is the midpoint of BC. Why? Because at point M, BC, side BC has been bisected into two halves. The first half is BM, and it is of course equals to the second half of BC, that is MC. And each half must be equal to BC over 2, because BC has been bisected into two halves. So, I write it down, we should find out that point M is the midpoint of BC. That is to say, at point M, BC has been bisected into two halves. The first half of BC is BM, and it is of course equals to the second half of BC, that is MC, and each half must be equal to BC over 2, because at point M, BC has been bisected into two halves. So in total, we should find out that BM equals to MC equals to BC over 2. BC in total equals to BQ, that is 10, plus QC, that is 40. So in total, BC equals to 10 plus 40, that is 50. So BC equals to 10 plus 40 over 2. 10 plus 40 is 50, and 50 over 2 is 25. From this long equation, BM equals to MC equals to BC over 2 equals to 10 plus 40 over 2 equals to 50 over 2 equals to 25. From this long equation, we will derive that BM equals to MC equals to 25. This is line segment BM that equals to 25 units in its length. Likewise, this is line segment MC that is also equals to 25 units in its length. What is the length of this missing line segment? Line segment QM. From the drawing, it is very easy to see that QM in total equals to BM over BQ. Again, BM over BQ equals to QM. So, I'll write it down. Now we found out that the missing side QM equals in total to BM minus BQ. So QM in total equals to BM, that is 25, minus BQ, that is 10, according to what is given in the question. So QM in total equals to 25 minus 10, that is 15. QM equals to 15 units in its length. This is the instrument QM that equals to 15 units in its length. In the next step, we will implement the Pythagoras theorem on this right triangle QPM. And again, we will implement the Pythagoras theorem on this right green triangle QPM. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. So in this right triangle QPM, according to the Pythagoras theorem, PM squared, that is the square of the hypotenuse, is equal to QM squared plus QP squared. And again, according to the Pythagoras theorem, in this right green triangle QPM, PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. PM is the missing side, so leave it as it is. So it is PM squared equals to QM squared. QM is 15, and therefore QM squared is 15 squared, that is 225, plus QP squared. QP is 20, and therefore QP squared is 20 squared, that is 400. So in total, we should find out that PM squared equals to 225 plus 400, that is actually 625. So in total, we should find out that PM squared equals to 625. Here we take a root out of this equation and find again that the length of the hypotenuse PM is equal to the square root of 625, that is 25. So in total we should find out that PM, the hypotenuse PM equals to 25 units in its length. In the next step, we will do another construction, that is to say, from this point M, we will do perpendicular on DC. Again, from point M, we will do perpendicular on DC. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point M and DC, this point is point N. By doing this construction, we're going to do quadrilateral PM and D. Inside quadrilateral PM and D, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral PM and D we have 4 right angles, and therefore quadrilateral PM and D is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PM and D, side PM must be equal to the opposite side DN. But PM is 25, and therefore the opposite side DN must be also equal to 25 units in its length. In the next step, we will define this angle. It is actually angle QPM as alpha. And we focus on this green right triangle QPM. On this green right triangle QPM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. BC is one side of quadrilateral ABCD, and therefore BC is a side of a quadrilateral. It is absolutely a straight line. So if you focus on the left side of the straight line BC, it's point M. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line BC at point M? We have this angle that is equal to 90 degrees minus alpha, plus this angle that is right angle, plus this first angle. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. So 90 degrees minus alpha plus 90 degrees and 180 degrees minus alpha. So the sum of those two angles is, in total is 180 degrees minus alpha. So 180 degrees minus alpha plus the size of this third missing angle in total must be equal to 180 degrees according to rule 3. Therefore, this third missing angle must be equal to alpha. What was 180 degrees minus alpha plus alpha is 180 degrees. This is the sum of the angles on the left side of the straight line BC at point M according to rule 3. Therefore, this third missing angle must be equal to alpha. In the lower right triangle M and C, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. According to the sum rule, it said that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that this green triangle PQM, can go into this right lower triangle M and C according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, PM, side PM of this right triangle PQM equals to side MC of this right triangle M and C. Both are hypotenuses, they are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So in total, we should prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we prove that those two angles and the side that is included between those two angles, that is side PM, this green right triangle QPM, are corresponding equal to those two angles, and the side that is included between those two angles, that is actually side MC in this right triangle MNC. And therefore, those two right triangles can go into each other according to angle side angle rule. So I'll write it down and should prove that this is the right triangle PQM. It's congruent. This is the sign of congruent to this right lower triangle MNC according to angle side angle rule. Okay, again, actually found out that the upper right green triangle PQM can point to the right lower triangle MNC according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that those two corresponding sides must be also equal to each other in their lengths. According to the rule that corresponding sides in congruent triangles are equal to each other, those two right triangles can go into each other, and therefore those two corresponding sides, that is to say QP and MN, must be also equal to each other in their lengths. But QP is 20, and therefore the corresponding side MN must be also equal to 20 units in its length according to the rule that I mentioned. So MN equals to 20. Likewise, in those two congruent triangles, those two corresponding sides must be also equal to each other in their lengths according to the same rule. So that is to say QM, that is equal to 15, must be equal to the corresponding side NC. So QM equals to 15, and therefore the corresponding side NC must be also equal to 15 units in its length, according to the rules they mentioned. So in total, we should find out that the length of this side DC of quadrilateral ABC equals to DN, that is 25, plus NC, that is 15. 25 plus 15 is 40. So DC equals to 40 units in its length. This is side AB, that is the missing side. And here we have in rectangle PM and D, the opposite sides are equal to each other. That is to say, side MN must be equal to the opposite side PD, that is equal to X. But MN is 20, therefore the opposite side PD, that is equal to X, must be also equal to 20 units in its length. So X equals to 20, and because of the fact that X equals to 20, here AP is equal to X, must be also equal to 20 units in its length. So, as I already mentioned before, the perimeter of this quadrilateral ABCD equals to the sum of its four side lengths. So we have all those three sides, you know, the length of those three sides. The only missing side that is left to find is to find out the length of this side AB, that is the missing side. In order to find out the length of side AB, we will implement the trapezoid mid-segment theorem on this quadrilateral ABCD. First of all, quadrilateral ABCD is a trapezoid. Why? Because a trapezoid is defined as a quadrilateral with one pair of parallel sides. This quadrilateral ABCD, we have one pair of sides that are parallel to each other. That is to say, side AB is parallel to the opposite side DC according to rule 18. Again, AB is parallel to DC according to rule 18, and therefore quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. So in trapezoid ABCD, we'll focus on this line segment PM. PM bisect. First of all, the two parallel sides AB and DC are defined as the bases of this trapezoid ABCD, while the two other sides AD and BC that are not parallel to each other, they are defined as the legs of this trapezoid ABCD. So AD is the leg of this trapezoid ABCD, BC is also the leg, AB and DC are defined as the bases of trapezoid ABCD. Line segment PM bisect those two legs AD and BC. Why line segment PM bisect AD? Because point P is the midpoint of AD. It's point P, side AD has been bisected into two halves. The first half is AP, that is 20, and it is equal to the second half, PD, it is also 20. So point P, line segment AD has been bisected into two halves. Each half equals to 20. Likewise, the same line segment PM bisect the leg BC. Why? Because point M is the midpoint of BC. Point M, BC has been bisected into two halves. The first half is BM, that is 25, and it is of course equals to the second half of BC, that is MC, that is also 25. So in total, I can say in conclusion that PM bisects both legs AD and BC, and therefore PM is defined as the mid-segment of trapezoid ABCD because it bisects both legs AD and BC. And according to the trapezoid mid-segment theorem, the length of side PM is equal to the sum of its two parallel bases, that is to say AB plus DC over 2. So I write it down. According to the trapezoid mid-segment theorem, the mid-segment PM of trapezoid ABCD bisect the two legs AD and BC of trapezoid ABCD, and therefore the length of PM in total it is equal to the sum of its two parallel bases, that is to say AB plus DC over 2. Repeat again. According to the trapezoid mid-segment theorem, the length of this mid-segment PM in total is equal to the sum of its two parallel bases, that is to say AB plus DC over 2. But we already found out that the mid-segment PM equals to 25, so we'll substitute PM by 25. And it is equals to AB. AB is the missing side, so we'll leave it as it is. Plus DC. DC in total is 25 plus 15, that is 40, so we'll substitute DC by 40 over 2. So in total, according to the trapezoid mid-segment theorem, we found out that 25 equals to AB plus 40 over 2. Here we will multiply this equation by 2 and finally get that 25 times 2 is 50. So 50 equals to AB plus 40. Here we subtract 40 from this equation and finally get that the missing side AB is equal to 50 minus 40, that is 10. Total, we found out that AB equals to 10 units in its length. This is the missing side AB is equals to 10 units in its length. Now we can find out the perimeter of this trapezoid ABCD. This actually can be defined as also quadrilateral ABCD. So as I mentioned before, the perimeter of quadrilateral ABCD equals to the sum of its four side lengths. So the perimeter of quadrilateral ABCD or trapezoid ABCD in total it is equal to the sum of its four side lengths. That is to say, it is AB plus AD plus side DC plus side BC. So in total, if we found out that the perimeter of quadrilateral ABCD equals to AB plus AD plus DC plus BC. We just right now found out that AB is 10 plus AD. AD in total equals to 20 plus 20, that is 40, plus DC. DC in total equals to 25 plus 15, that is 40, plus BC. BC in total equals to 10 plus 40, that is 50. So in total, she found out that the perimeter of quadrilateral ABCD equals to 10 plus 40 plus 40 plus 50. 10 plus 40 is 50, 50 plus 40 is 90, 90 plus 50 is 140. So the perimeter of quadrilateral ABCD in total it is equal to 140 units in its length. That is the answer to the question. Okay, again, we found out that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. In the next step, I will present to you a second method that will help us to find out the length of this side AB. We find out in the second method that AB indeed equals to 10 units in its length. In the first method, we found out that AB equals to 10 units in its length by implementing the trapezoid mid-segment theorem on this trapezoid ABCD. In the second method, we find out that AB equals to 10 units in its length in a different way. That is to say, we do a construction here. From point B, we do perpendicular on PM. Again, from point B, we do perpendicular on PM. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We define the touching point of the perpendicular from point B and PM. This point is point S. found out that PM equals to 25 units in its length. So by doing this construction, we're going to do quadrangle ABSP. Inside this quadrangle ABSP, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the side of this fourth missing angle, total must equal to 360 degrees. According to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this fourth missing angle must be equal to 9 degrees in its side according to the rule that I mentioned. So in quadrangle ABSP we have 4 rectangles, and therefore quadrangle ABSP is a rectangle. But we also know that the opposite, but before that we'll focus on this right triangle BSM. On this right triangle BSM, this angle equals to 90 degrees, alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to alpha. According to the rule that said that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we will prove that the upper right triangle BSM can go into this lower right triangle MNC according to side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha and therefore they are equal to each other. In addition, BM, the hypotenuse BM of this right triangle BSM equals to the hypotenuse MC of this right triangle MNC. They are both equal to 25 and therefore they are equal to each other. Repeat again. BM equals to MC, but they are both equal to 25 units in their lengths and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees alpha and therefore they are equal to each other. So if you prove that those two right triangles can go into each other according to angle side angle rule, that is to say, if you prove that those two angles and the side that is included between those two angles that is actually side BM, in this right upper triangle BSM are corresponding equal to those two angles, and the side that is included between those two angles that is side MC, in this right lower triangle MNC. Therefore, if you prove that those two right triangles can go into each other according to angle side angle rule. So I'll write it down. If you prove that this is the right triangle BSM, the right upper triangle BSM, it can go to this right lower triangle MNC according to angle side angle rule. Okay, again, if you found out that the upper right triangle BSM can go into the right lower triangle MNC according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that their corresponding sides SM and NC must be also equal to each other in the lengths according to the sum rule that I mentioned a couple of times, that says that corresponding sides and right triangles are equal to each other. Those two triangles can go into each other, and therefore their corresponding sides, that is to say SM and NC, must be also equal to each other in their lengths. But NC is 15, and therefore the corresponding side SM must be also equal to 15 units in itself according to the rule that I mentioned. So M equals to 15 units in its length. What is the length of this missing line segment? Line segment PS. From the moment it is very easy to see that PS in total equals to PM minus SM. So it is now. Once we found out that PS in total equals to PM minus SM. So PS in total equals to PM, that is 25, minus SM, that is 15. So in total PS equals to 25 minus 15, that is 10. PS equals to 10 units in its length. This is the missing side PS. This equals to 10 units in its length. So in this rectangle, AB as P, the opposite sides are equal to each other. That is to say, side PS equals to the opposite side AB, but PS is 10, therefore the opposite side AB must be also equal to 10 units in its length. So we proved in two different ways that AB equals to 10 units in its length, and the answer to the question is that the perimeter of this quadrilateral ABCD is equal to 140 units in its length. So we finished to answer the first question. In the next step I present to you the second question, and we'll solve the second question of this lecture. Our task in this second question is to find out the area of this green shape. So in the drawing we have two semicircles. This is the big semicircle. Inside this big semicircle we have this small semicircle. Again, our task is to find out the area of this green shape. So first of all, we will define the center of this big semicircle. This point is point O. Likewise, we will define the center of this small semicircle. This point is point S. We define the radius of this small semicircle as x. So the radius SP equals to x. The radius SQ of this small semicircle also equals to x units in its length. What is the radius of this big semicircle? We know that the diameter AB in total equals to AC, that is 4, plus CB, that is 6. So in total the diameter AB of this big semicircle equals to 4 plus 6, that is 10. So, and then if we found out that the diameter AB of this big semicircle in total it is equals to 4 plus 6, that is 10. We define the radius of this big semicircle as capital R. So capital R, the radius of the big semicircle, must be equal to the diameter AB over 2. That is to say it is 10 over 2, that is 5. Total, we found out that the radius of the big semicircle, capital R, is equal to 5 units in its length. In the next step, we will join points S and C together by straight line. Point S is the center of this small semicircle. Point C is the point of the small semicircle itself. Therefore, SC is the radius of this small semicircle. That is equal to x units in its length according to our definition. Here we can implement all one because we have here point C is the point of tendency of tangent AB with this small semicircle. The radius SC is equals to x. The radius SC is drawn to point C, that is the point of tendency of tangent AB with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to rule 1. In the next step, we'll do another construction. That is to say, from this point P, that is the touching point between this small semicircle and this big semicircle. So from point P, we will draw perpendicular on AB. Again, from point B, we draw perpendicular on AB. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point P and AB. This point is point M. What is the definition of line segment MP? Line segment MP is a tangent to the small semicircle at point P. Therefore, MP is a tangent to this small semicircle. This is the radius SP. The radius SP is equals to X. The radius SP is drawn to point P. That is the point of tendency of the MP with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent MP will be perpendicular to the radius PS. If MP is perpendicular to PS, it means that this angle equals to 90 degrees according to rule 1. So in total, inside the small quadrilateral PSCM, we have 1, 2, 3 angles, and therefore this 4 piece angle must be equal to 90 degrees inside, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral PSCM, we have 4 angles, and therefore we can define, you can say quadrilateral PSCM as a rectangle because it has 4 rectangles. So okay, now quadrilateral PCMC is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in this rectangle, small rectangle PCCM, side PS must be equal to the opposite side MC, but PS is X, therefore the opposite side MC must be also equal to X units in its length. Likewise, according to the sum rule, in the same rectangle PSCM, side SC must be equal to the opposite side PM, but SC is X, therefore the opposite side PM must be also equal to X units in its length. What is the length of this short line segment? Line segment AM. From the drawing, it is very easy to see that AM in total must be equal to AC, that is 4, minus MC, that is X. So if you found out that AM in total, the short line segment AM, in total it is equal to AC minus MC. So AM in total must be equal to AC, that is 4, according to what is given as the question, minus MC. We just right now found out that MC equals to X. So in total, AM equals to 4 minus X units in its length. This is the short line segment AM. This equals to 4 minus X units in its length. In the next step, we will do a construction. That is to say, we will complete this big semicircle to a circle. So completed the semicircle to a circle. Then we'll extend tangent PM by straight line until it touches the circle. We define the touching point of the extended tangent PM with this circle. This point is point N. PM is a tangent and therefore it is absolutely a straight line. When you extend a straight line by straight line, the result is a straight line. If you extended the straight line PM by straight line, the result PN must be also a straight line. So PN is a straight line. If you focus on the right side of the straight line PN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles do we have at the right side of the straight line PN at point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in size. Point O is the center of this big circle. From point O, we have perpendicular OM on chord PN. Again, from point O, that is the center of this big circle, we have perpendicular OM on chord PN. And according to rule 15, a perpendicular from the center of the circle towards any chord bisect the chord. Again, a perpendicular from the center of the circle towards any chord will bisect the chord. Repeat quickly on rule 15. According to rule 15, a perpendicular from the center of a circle towards any chord bisect the chord. In the moment we have a circle, point S, the center of this circle. From point S, we have perpendicular ST on chord MN. Again, from point S, that is the center of this circle, we have perpendicular ST on chord MN. And according to this rule 15, perpendicular ST bisect chord MN. That is to say, ST divides chord MN into two halves. The first half is MT, and it is of course equal to the second half Tn, and each half must be equal to Mn over 2 because Mn is being bisected into two halves by St. So in total, I can found out that the first half of MT, the first half of chord Mn is MT, and it is equal to the second half of chord Mn, that is Tn, and each half must be equal to Mn over 2 because Mn is being bisected by two Mn is bisected into two halves by St. So Mt equals to Tn equals to Mn over 2. Can implement rule 15 in our drawing. One put in our drawing, from the center of this big circle, we have perpendicular OM on chord Pn. According to rule 15, perpendicular OM bisects chord Pn. If OM bisects chord Pn, it means that it divides chord Pn into two halves. The first half of Pn is Pm, and it is of course equal to the second half of Pn, that is Mn. So according to rule 15, Pm, this is the first half of Mn, this is the first half Pm, that is the first half of Pn, equals to the second half of Pn, that is Mn. So Pm equals to Mn, according to rule 15. But we already found out that Pm equals to x. So we can write here that Pm equals to x, and from this equation x equals to Pm equals to Mn, we will derive that Mn also equals to x units in its length. This is side Mn that equals to x units in its length according to rule 15. So, moving on, mn equals to x units in its length. In the next step, we will implement rule 24 in our drawing. So I'll repeat quickly on rule 24. Rule 24 is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times BO equals to CO times DO. In the drawing we have a circle, this is chord AB that intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So in this drawing, whenever we have two chords that intersect with each other inside the circle, then the following equation is true. That AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement all 24 in our drawing. When put in our drawing, this is chord AB, that is actually the diameter of this big circle. Chord AB intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. So all the requirements for rule 24 are satisfied, and therefore we can implement a rule 24. So, as you know, we found out that in our original drawing, chord AB intersects with chord PN, and the intersection point occurs at point M. Therefore, we can implement here rule 24. According to rule 24, the following equation is true. AM times MB equals to PM times MN. So until now, if you found out that according to 24, the following equation is true. AM times MB equals to PM times Mn. Repeat again, if you found out that according to rule 24, the following equation is true. AM times MB equals to PM times Mn. This equation is the implementation of rule 24 in our drawing. AM is 4 minus x. Minus MB. MB in total equals to MC, that is x, plus CB, that is 6. So in total, MB equals to x plus 6 units in its length. So we substitute MB by x plus 6. And it is equals to PM, PM is x, times MB times MN, that is also x. X times x is x squared. So in total, we shall find out that 4 minus x times x plus 6 equals to x squared. Here we will open the brackets on this side of this equation, and get that 4 times x is 4x. Plus 4 times 6 is 24, minus x times x is minus x squared, minus x times 6 is minus 6x, equals to x squared. So in this side of the equation we have 4x minus 6x is minus 2x, plus 24 minus x squared equals to x squared. So in total we actually found out that according to rule 24, minus 2x plus 24 minus x squared equals to x squared. Here we will add x squared to this equation. So in this side of the equation we have x squared minus x squared is 0. And in this side of the equation we left only minus 2x plus 24 equals to, this of the, on the other side of the equation we have x squared plus x squared, that is 2x squared. So in total we found out that minus 2x plus 24 equals to 2x squared. Here we will add 2x to this equation and finding out that here 2x minus 2x is 0, so here we left only, in this side of the equation, on this side of the equation we left only with 24 equals to 2x squared plus 2x. Then again in total we found out that 24 equals to 2x squared plus 2x. Here we subtract 24 from the equation and get the total. In this side of the equation we have 2x squared plus 2x minus 24 equals to 0. Here we will divide this equation by 2 and we get that 2x squared over 2 is x squared plus 2x over 2 is x minus 24 over 2 is minus 12 equals to 0 over 2 is 0. So in total we found out that x squared plus x minus 12 equals to 0. So this is a quadratic equation and the general formula for a quadratic equation is as follows. Ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say, x squared plus x minus 12 equals to 0, the variable that we are looking for is x. X is the radius of this small semicircle. So, unknown, we are looking for the variable x, that is the radius of the small semicircle. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b also equals to 1, and the coefficient c equals to minus 12. So we actually have all the data that is needed in order to find out the value of x, that is the radius of the small semicircle. We just have to put the data of our specific quadratic equation inside this general formula for x. In this way, we'll find out the value of the values of x, that is the radius of the small semicircle. So we will do it now, and we will get that here x equals to minus b. b is 1, so minus b is minus 1, plus minus square root of b squared. b is 1, so b squared is 1 squared, that is 1, minus 4 times a times c. So it is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c is minus 12, so minus 4 times minus 12 is plus 48. So in total inside the root we have 1 plus 48 over 2a. a is 1, so 2 times a is 2 times 1, that is 2. So in total we actually found out that x equals to minus 1 plus minus 48 plus 1 is 49 over 2. So in total we actually found out that x equals to minus 1 plus minus, the square root of 49 is 7 over 2. And again in total we actually found out that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for the value of x. The first solution for x is as follows: x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. So the first solution for x is that x equals to minus 4. But x can never be equal to minus 4. Why? Because x is the radius of this small semicircle. That is to say, x is the length, and therefore it must be a positive number. So x can never be equal to minus 4. That is a negative number. So we will cancel the first solution for x, and we will take into account only the second solution for x. The second solution for x is as follows: x equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. So the second solution for x is that x equals to 3 units in its length. This is to say that we found out that the radius x of this small semicircle equals to 3 units in its length. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it's very easy to see that the area of the green shape in total equals to the area of the big semicircle minus the area of this small semicircle. So, the area of the green shape in total must be equal to the area of the big semicircle minus the area of the small semicircle. We already found out that the radius of this big semicircle equals to 5 units in its length, and the radius of this small semicircle equals to 3 units in its length. And therefore, the area of the big semicircle must be equal to pi r squared over 2. R is 5, so it is pi times 5 squared over 2. That is the area of the big semicircle minus the area of the small semicircle. If we reduce 3, and therefore the area of the small semicircle in total must be equal to pi times 3 squared over 2. Here we take 2 as a common factor out of those two expressions. So in the numerator of this expression we have in total 25 pi, minus in the numerator of this expression we have 9 pi over 2. 25 pi minus 9 pi is 16 pi. 16 pi over 2 is 8 pi. So in total we should find out that the area of the green shape, that is the area that we are looking for this question, is equal to either 8 pi square units in size, or in terms of numbers it is equal to 25.13 square units in size. If again, we should know that the area that we are looking for this question, that is the area of this green shape, it is equal to either 8 pi square units in size, or in terms of numbers, the area of this green shape equals to 25.13 square units in size. So we finished to answer on the second question. In the next step on some other lecture, that is to say, we will repeat on the solution of the first question, and then we will repeat on the solution of this second question. on the first question, our task is to find out the perimeter of this quadrilateral ABCD. The perimeter of any quadrilateral is equal to the sum of its four side lengths. That is to say, it is equal to AB plus AD plus DC plus CB. So we have to find out the perimeter of this quadrilateral ABCD. In the drawing, we have the big quadrilateral ABCD. We know that this is the small line 7BQ, that is equal to 10 units in its length. This is line 7QP, that is equal to 20 units in its length. This is line 7QC, that is equal to 40 units in its length. Those three angles are all right angles. Again, our task is to find out the perimeter of this quadrilateral ABCD. That is actually equal to the sum of its four side lengths. So in the first step, we did a construction, that is to say, we draw perpendicular on side AD, it's point P. Again, it's point P, we draw perpendicular on side AD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We extended the perpendicular from point P by a straight line until it touches side BC. And we find the touching point of the extended perpendicular from point P and side BC. This point is point M. So here, by doing this construction, we created this right angle. Those two angles are both defined as one-sided interangles, and the sum of those two one-sided interangles is equal to 180 degrees, and therefore according to Rule 18, they must be located between parallel lines. That is to say, AB is parallel to PM. So I print quickly on Rule 18. According to Rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they lie between parallel lines. Those two angles alpha and beta, they are both defined as one-sided interangles. If the sum of those two one-sided interangles is equal to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then they must be located between parallel lines. That is to say, then line A will be parallel to line B. Again, if the sum of those two one-sided interangles is equal to 180 degrees, that is to say, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. So, as mentioned before, we can implement Rule 18 in our drawing. Well, in our drawing, the sum of those two one-sided interangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, AB is parallel to PM. So, if we found out that AB is parallel to PM, according to Rule 18. Likewise, the sum of those two one-sided interangles is equal to 180 degrees, and therefore according to Rule 18, those two one-sided interangles must be located between parallel lines. That is to say, PM is parallel to DC. Then again, if we found out that PM is parallel to DC according to the same rule, Rule 18. Likewise, the sum of those two one-sided interangles in total is equal to 180 degrees, and therefore those two one-sided interangles must be located between parallel lines. That is to say, AB is parallel to DC. AB is parallel to DC according to the same rule, Rule 18. So in total, we found out that all those three line segments, AB and PM and DC, they are parallel to each other. So we have here three parallel lines. AB is parallel to PM, is parallel to DC. This is the side AD that connects the three parallel lines together. Likewise, this is side BC that connects those three parallel lines together. And according to the basic proportionality theorem, a special relationship exists between AD and BC that connects those three parallel lines together. The relationship is as follows. AP over PD equals to BM over MC. Again, AP over PD equals to BM over MC. So according to the basic proportionality theorem, whenever you have three or more line segments that are parallel to each other, and we have other two line segments that connect the three parallel lines together, a special relationship exists between the two line segments that connect the three parallel lines together. The relationship is as follows. AP over PD equals to BM over MC. It's given us the equation that AP equals to PD. So if we define AP as X, then PD must be also equal to X because they are equal to each other. Therefore, AP over PD equals to X over X. This is equals to BM over MC. X over X is 1, so 1 equals to BM over MC. Here we multiply this equation by MC and finally found out that MC equals to BM. MC equals to MB. BM. So that is to say, side BC has been bisected into two halves at point M. Point M is the midpoint of BC. If BC has been bisected into two halves at point M, it means that the first half of BC is BM, and it is of course equal to the second half of BC, that is MC, and each half must be equal to BC over 2 because BC has been bisected into two halves. So in total we should find out that BM equals to MC, according to the basic proportionality theorem, and point M is the midpoint of BC. That is to say, at point M, BC has been bisected into two halves. The first half is BM, and it is of course equal to the second half, that is MC, and each half must be equal to BC over 2 because BC has been bisected into two halves at point M. But what is the value of BC? BC in total equals to BQ, that is 10, plus QC, that is 40. So BC in total equals to 10 plus 40, that is 50. So again, BC in total equals to 10 plus 40, that is 50 over 2. 50 over 2 is 25. So in total from this long equation, BM equals to MC equals to 25. We derive from this long equation that BM equals to MC equals to 25. BM equals to MC equals to 25. That is to say, BM equals to 25 units in its length, and MC must also equal to 25 units in its length. In the next step, we found out the length of this missing line side, QM. BM is 25. BQ is 10, and therefore QM in total must be equal to BM plus QM. Again, QM in total equals to BM minus BQ. Again, QM equals to BM minus BQ. QM equals to BM minus BQ. So QM equals to BM, that is 25, minus BQ, that is 10. So in total QM equals to 25 minus 10, that is 15. The missing line side QM equals to 15 units in its length. In the next step, we implemented the Pythagoras theorem on this green right triangle PQM. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In this green right triangle PQM, PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. But again, this right triangle PQM, according to the Pythagoras theorem, the following equation is true. PM squared, that is the square of the hypotenuse, equals to QM squared plus QP squared. PM is the missing side, so it is. So it is PM squared, and it is equal to QM squared. QM is 15, and therefore QM squared is 15 squared, that is 225. Plus QP squared. QP is 20, and therefore QP squared is 20 squared, that is 400. So in total, we should find out that PM squared equals to 225 plus 400. Okay, again, in total, we should find out that PM squared equals to 225 plus 400, that is 625. So PM squared equals to 625. Here we took out of this equation and found out that the length of the hypotenuse PM is equal to the square root of 625, that is 25. This is the hypotenuse PM, that is equal to 25 units in its length. In the next step, we defined the size of this angle QPM. This angle is alpha. So in the green right triangle PQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha. Well, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in any triangle. BC is one side. So in the next step, we did the construction, that is to say, from point M we do perpendicular on DC. Again, from point M we do perpendicular on DC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point M and DC. This point is point M. It's point N. By doing this construction, we can do quadrilateral PM and D. Inside quadrilateral PM and D, we have 1, 2, 3 rectangles, and therefore this fourth missing angle must be equal to 90 degrees in this side according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral PM and D, we have 4 rectangles, and therefore quadrilateral PM and D is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle PM and D, side PM must be equal to the opposite side ND. But PM is 25, and therefore the opposite side ND must be also equal to 25 units in itself. BC is one side of quadrilateral ABCD, therefore as a side of a quadrilateral it is absolutely a side line. So BC is the side line. If you focus on the right side of the side line BC at point M, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the angles on one side of a side line is equal to 180 degrees. So which angles we have at the left side of the side line BC at point M? We have this angle that is equal to 90 degrees 1 alpha. 90 degrees 1 alpha. This angle is the right angle plus this third missing angle. In total, the sum of those three angles must be equal to 180 degrees according to Rule 3. Therefore, this third missing angle must be equal to alpha. Why? Because 90 degrees minus alpha plus 90 degrees is 180 degrees minus alpha. So the sum of those two angles, in total, it is 180 degrees minus alpha. 180 degrees minus alpha plus this missing angle, in total, must be equal to 180 degrees. And therefore, this missing angle must be equal to alpha. Why? Because 180 degrees minus alpha plus alpha is equal to 180 degrees. It is the sum of the angles of the left side of the side line BC at point M according to Rule 3. Therefore, this third missing angle must be equal to alpha. So in this right lower triangle, and M and C, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus alpha, according to the sum rule that said that the sum of the angles in a triangle is equal to 180 degrees. In the next step, we prove that those two right triangles, that is to say, this is the right triangle PQM, and this is the right lower triangle M and C. We prove that those two right triangles can go into each other according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, PM equals to 25, MC also equals to 25, and therefore those two sides are both equal to 25, or those two hypotheses are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees alpha, and therefore they are equal to each other. So we should prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we should prove that those two angles and the side that is included between those two angles, that is side PM, in this green right triangle PQM, are corresponding equal to those two angles and the side that is included between those two angles, that is side MC, this right lower triangle M and C. Therefore, those two right triangles can go into each other according to angle side angle rule. Okay, again, we can find out that the upper green triangle PQM congruent, this is the sum of congruent to the right lower triangle M and C according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that those two corresponding sides must be also equal to each other in their lengths, according to the rule that says that corresponding sides and congruent triangles are equal to each other. Those two right triangles can go into each other, and therefore those two corresponding sides must be also equal to each other in their lengths. But QP is 20, therefore the corresponding side MN must be also equal to 20 units in its length. Likewise, according to the sum rule, those two corresponding sides must be also equal to each other in their lengths. But QM is 15, and therefore the corresponding side NC must be also equal to 15 units in its length. So in total, DC equals to 25 plus 15, that is 40. AB is the missing side. So here we have quadrilateral ABCD. Quadrilateral ABCD is a trapezoid. Why? Because the definition of a trapezoid is a quadrilateral with one pair of parallel sides. The quadrilateral ABCD, we have side AB is parallel to side DC according to Rule 18, and again, AB is parallel to DC, therefore quadrilateral ABCD that has one pair of parallel sides, it is defined as a trapezoid. So we have here trapezoid ABCD. The two parallel sides, that is to say AB and DC, are defined as the bases of this trapezoid, while the other two sides that are not parallel to each other, that is to say AD and BC, are defined as the legs of this trapezoid ABCD. You have here line segment PM. Line segment PM bisect the leg AD and also bisect the leg BC. Why PM bisect the leg AD? Because point P is the midpoint of AD. That is to say, at point P, AD is bisected into two halves. The first half is AP, and it is of course equals to the second half PD. Likewise, point M is the midpoint of BC. So at point M, line 7 PM bisect the leg BC, point M. The first half of BC is BM, that is 25, and it is of course equals to the second half of BC, that is MC, that is also 25. So in conclusion, you can say that line 7 PM bisect both legs AD and BC of this trapezoid ABCD, and therefore line 7 PM is defined as the mid segment of trapezoid ABCD because it bisects the two legs AD and BC. Actually, the mid-segment trapezoid theorem talks about the left, of mid-segment PM that bisects the two legs AD and BC. According to the trapezoid mid-segment theorem, the left of PM total equals to the sum of its two parallel bases, that is to say AD plus DC over 2. And again, according to the trapezoid mid-segment theorem, the length of the mid-segment PM that bisects the two legs of the trapezoid, in total it is equals to the sum of its two parallel bases, that is actually AB plus DC over 2. AB is the missing side, so leave it as it is. Plus DC. DC in total equals to 25 plus 15, that is 40. So substitute DC by 40 over 2. We already found out that the mid-segment PM equals to 25 units in itself, so therefore we substitute PM by 25. So in total we found out that according to the trapezoid mid-segment theorem, 25 equals to AB plus 40 over 2. Here we multiply this equation by 2 and finally found out that 25 times 2 is 50, so 50 equals to AB plus 40. Here we subtract this 40 from this equation and finally found out that the missing side AB equals to 40 minus 50 minus 40, that is 10. This is the missing side AB, this is equals to 10 units in itself. So our test is to find out the perimeter of this trapezoid ABCD, then is actually also quadrilateral ABCD. The perimeter of any quadrilateral equals to the sum of its four side lengths. That is to say, the perimeter of this quadrilateral ABCD must be equal to AB plus AD plus DC plus BC. And again, our test is to find out the perimeter of this quadrilateral ABCD, that total is equals to the sum of its four side lengths. That is to say, it is equals to AB plus AD plus DC plus BC. So the perimeter of this quadrilateral ABCD equals to AB, that is 10, plus AD, that is 40, plus DC, that is also 40, plus BC, that is 50. So in total, the perimeter of quadrilateral ABCD equals to 10 plus 40 plus 40 plus 50. 10 plus 40 is 50, 50 plus 40 is 90, 90 plus 50 is 140. So in total, we found out that the perimeter of this quadrilateral ABCD, that is the perimeter that we are looking for in this question, in total it is equal to 140 units in its length. In the next step, I presented to you a second method to find out that AB equals to 10. According to the first method, we found out that AB equals to 10 by implementing the trapezoid mid-segment theorem in our drawing. So in the second method, we found out that AB equals to 10 by doing a construction, that is to say from point B we do perpendicular on PM. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the tangent points of the perpendicular from point B and PM. This point is point S. By doing this construction, we can deduct quadrilateral ABSP. Inside quadrilateral ABSP, we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees. And inside, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral ABSP, we have 4 angles, and therefore quadrilateral ABSP is a rectangle. So in this upper right triangle BSM, this angle equals to 90 degrees according to our construction. This angle equals to 90 degrees minus alpha according to all three. And therefore, this first missing angle must be equal to alpha. 1 equals 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, and that is the sum of the angles in a triangle. In the next step, we prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we prove that this upper right triangle BSM can go into this lower triangle MNC according to angle side angle rule. So why those two right triangles can go into each other? First of all, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, BM equals to MC. The hypotenuse of those two right triangles are both equal to 25, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees on alpha, and therefore they are equal to each other. So we can prove that those two right triangles can go into each other according to angle side angle rule. That is to say, we prove that those two angles and the side that is included between those two angles, that is side BM, in this right triangle BSM, corresponding equal to those two angles, and the side that is included between those two angles, that is side MC, in this right lower triangle MNC. Therefore, those two right triangles can go into each other according to angle side angle rule. Again, we should prove that the upper right triangle BSM can go in, this is the sign of can go in, to the right lower triangle MNC according to angle side angle rule. And from the fact that those two right triangles can go into each other, we know that those two corresponding sides must be also equal to each other in the left. According to the formula that I mentioned a couple of times, that corresponding angles can corresponding sides and can go triangles are equal to each other. Those two triangles can go into each other, and therefore their corresponding sides SM and NC must be also equal to each other in their lefts. But NC is 15, and therefore its corresponding side SM must be also equal to 15 units in itself, according to the rule that I mentioned. So in total, PS equals to PM minus SM. Again, PS equals to PM minus SM. PS equals to PM minus SM. So PS in total equals to PM, that is 25, minus M, that is 15. So in total, PS equals to 25 minus 15, that is 10. So PS equals to 10 units in its length. In rectangle ABSP, side PS equals to the opposite side AB, but PS is 10, therefore the opposite side AB is also equals to 10 units in its length. So we prove that in two different methods that AB equals to 10 units in its length. And the final answer to the question is that the perimeter of this quadrilateral ABCD equals to 140 units in its length. So we finished to answer the first question. In the next step, I repeat on the solution of the second question. Our task in the second question is to find out the area of this green shape. So in the drawing we have two semicircles. This is the big semicircle. Inside this big semicircle we have this small semicircle. It is given us the question that the length of line 7AC is 4 units. This is line 7CB is equals to 6 units in its length. Again, our task is to find out the area of this green shape. First of all, we define the center of this big semicircle. This point is point O. Likewise, we define the center of this small semicircle. This point is point S. We define the radius of this small semicircle as x. So the radius SP equals to x. The radius SQ also equals to x. We have AB is the diameter of this big semicircle. AB in total equals to AC, that is 4, plus CB, that is 6. So in total, AB equals to 4 plus 6, that is 10. So the diameter AB of the big semicircle equals to 4 plus 6, that is 10. We define the radius of this big semicircle as R. So the radius R must be equal to the diameter AB over 2. That is to say it is 10 over 2, that is 5. So in total, we should find out that the radius R of this big semicircle equals to 5 units in its length. In the next step, we join points S and C together by a straight line. Point S is the center of this small semicircle. Point C is the point on the small semicircle itself. Therefore, SC is the radius of this small semicircle, that is equals to x. The radius SC is equal to x. The radius SC is drawn to point C, that is the point of tendency AB with this small semicircle. Whenever you order this don't do the point of tendency, then AB will be perpendicular to the other CS. If AB is perpendicular to CS, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we did another construction, that is to say, from point P we do perpendicular on AB. Again, from point P we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P. We define the touching point of the perpendicular from point P and AB. This point is point M. What is the definition of line segment MP? Line segment MP is a tangent to the small circle at point P. So MP is a tangent. This is the radius speed is equals to x. The radius speed of this small semicircle that is equals to x. The radius speed is drawn to point P. That is the point of tendency MP with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent MP will be perpendicular to the radius PS. If MP is perpendicular to PS, it means that this angle equals to 90 degrees according to rule 1. So in total, inside quadrangle P, the small quadrangle PSCM, we have 1, 2, 3 angles, and therefore this small angle must be equal to 90 degrees inside according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle PSCM, we have 4 angles. And therefore we can define quadrangle PSCM as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle PSCM, side PS must be equal to the opposite side MC. But PS is x, therefore the opposite side MC must be also equal to x units in its length. Likewise, according to the sum rule, in the same rectangle PSCM, side SC must be equal to the opposite side PM. But SC is x, therefore the opposite side PM must be also equal to x units in its length. So if we found out that quadrangle SCM is not a rectangle but a square because of the fact that all of its sides are equal to each other, each side equals to x. What is the length of this short line segment AM? From the norm, it is very easy to see that AM in total equals to AC minus MC. AM equals to AC minus MC. So AM in total equals to AC, that is 4, minus MC, that is x. So in total, AM equals to 4 minus x units in its length. In the next step, we did the construction, that is to say, we completed this semicircle to a circle. Then we extended tangent PM by side line until it touches the circle. At this point, we define the touching point of the extended tangent PM with this circle. This point is point M. PM is a tangent, so PM is a tangent, it is absolutely a side line. When you extend the side line by side line, the result PN is a side line. So PN is a side line. If we focus on the right side of the side line PN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of the side line is equal to 180 degrees. So which angles we have at the right side of the side line PN at point M? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So in the drawing, this is point O, that is the center of this big circle. From point O, we have perpendicular OM on chord PN. Again, we have here perpendicular OM on chord PN. And according to rule 15, a perpendicular from the center of the circle towards any chord bisects the chord. Repeat quickly rule 15. According to rule 15, a perpendicular from the center of a circle towards any chord bisects the chord. In the drawing we have a circle. This is point S, that is the center of the circle. From point S we have perpendicular ST on chord MN. And according to this rule 15, perpendicular ST bisects chord MN. That is to say, it divides chord MN into two halves. The first half is MT, and it is of course equals to the second half of MN, that is TN. And each half must be equal to MN over 2 because MN has been bisected into two halves. So MT equals to TN equals to MN over 2. According to this rule 15. So we can actually implement rule 15 in our drawing. In our drawing, we have perpendicular OM from the center of the circle on chord PN. And according to rule 15, perpendicular OM bisects chord PN. This is to say, it divides chord PN into two halves. The first half is PM, and is of course equals to the second half, that is MN. And again, according to rule 15, perpendicular OM bisects chord PN. The first half of PN is and m, and it is of course equal to the second half of Pn, that is Pm. Again, the second half, the first half of Pn is Pm, and it equals to the second half of Pn, that is Mn. So Pm equals to Mn. But we already found out that Pm equals to x, so we can write here that Pm equals to x, and from this equation x equals to Pm equals to Mn, we will learn that Mn also equals to x units in its length. This is the mass inside Mn, this is equals to x units in its length. In the next step, we implemented rule 24 in our drawing. Okay, again, on rule 24, according to rule 24, rule 24 is true in any circle, so in any circle, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times BO equals to CO times DO. So in the drawing, we have a circle, this is chord AB that intersects with chord CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD, again AO times OB equals to CO times OD. So we can actually implement rule 24 in our drawing. In our drawing, we have chord AB, that is actually the diameter of this big circle. Chord AB intersects with chord PN at point M. Again, chord AB intersects with chord PN at point M. So all the requirements for full 24 are satisfied, and therefore we can implement here rule 24. So if we found out that in our original drawing, chord AB intersects with chord PN at point M. So all the requirements for rule 24 are satisfied, and therefore we can implement here rule 24. According to rule 24, the following equation is true, that AM times MB equals to PM times Mn. Again, AM times MB equals to PM times Mn. According to rule 24, AM times MB equals to PM times Mn. So this equation is the implementation of rule 24 in our drawing. AM is 4 minus x times MB. MB in total equals to MC, that is x, plus CB, that is 6. So in total, MB equals to 6 plus x units in its length. And then we found out that AM is 4 minus x, MB is 6x plus 6, and it equals to PM, that is x, times Mn, that is also x. So in total, PM times Mn equals to x times x, that is x squared. So in total, we found out that 4 minus x times x plus 6 equals to x squared. Here we open the brackets on this side of this equation, and find out that 4 times x is 4x, plus 4 times 6 is plus 24, minus x times x is minus x squared, and minus x times 6 is minus 6x equals to x squared. Here in this side of the equation we have 4x minus 6x is minus 2x, plus 24 minus x squared equals to x squared. So in total, minus 2x plus 24 minus x squared equals to x squared. Here we added x squared to the equation, so x squared minus x squared is 0. So in this side of the equation we have only response to x plus 24. But in this side of the equation, we have x squared plus x squared, this is 2x squared. So in total, we found out that 1 is 2x plus 24 equals to 2x squared. Here we added 2x to this equation, so in this side of the equation, we left only with 24 equals to 2x squared plus 2x. And then, in total, we found out that 24 equals to 2x squared plus 2x. Here we subtracted 24 from this equation, and finally found out that 2x squared plus 2x minus 24 equals to 0. Here we divided this equation by 2, and finally found out that 2x over 2 is x squared. 2x squared over 2 is x squared, plus 2x over 2 is x, minus 24 over 2 is minus 12, equals to 0 over 2 is 0. So in total we found out that x squared plus x plus 12 equals to 0. So this is the quadratic equation, and the general formula for quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say x squared plus x minus 12 equals to 0, the variable that we are looking for is x. X is the radius of this small semicircle, In our specific quadratic equation, the coefficient A equals to 1, the coefficient B also equals to 1, and the coefficient C equals to minus 12. So we have all the data that is needed in order to find out the value of x, that is the radius of the small semicircle. We just have to put our data inside this general formula for x. In this way, we find out the value of the values of x, that is the radius of the small semicircle. We actually did it. We found out that x equals to minus b. B is 1, so b is minus 1, plus minus square root of b squared. B is 1, so b squared is 1 squared, that is 1, minus 4 times a times c. So it is minus 4 times a is 1, so minus 4 times 1 is minus 4 times c. So minus 4 times, c is minus 12, so minus 4 times minus 12 is plus 48. So in total inside the root we have 1 plus 48, divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total we should find out that x equals to minus 1 plus minus 1 plus 48 is 49 over 2. The square root of 49 is 7. So in total we should find out that x equals to minus 1 plus minus 7 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to minus 1 minus 7 over 2. Minus 1 minus 7 is minus 8, and minus 8 over 2 is minus 4. But x can never be equal to minus 4 because x is the length of this radius of this small semicircle. So x is a length, and x as a length must be a positive number. It can never be equal to minus 4, that is a negative number. So we cancel the first solution for x, and we took into account only the second solution for x. The second solution for x is as follows. x equals to minus 1 plus 7 over 2. Minus 1 plus 7 is 6, and 6 over 2 is 3. So according to the second solution for x, that is the radius of this small semicircle, equals to 3 units in its length. Our task is to find out the area of this green shape. From the drawing, it is very easy to see that the area of this green shape equals to the area of the big semicircle minus the area of this small semicircle. Repeat again, the area that we are looking for in this question, that is the area of the green shape, in total is equals to the area of the big semicircle minus the area of the small semicircle. We already found out that the radius of the big semicircle equals to 5, and the radius of the small semicircle equals to 3. Therefore, the area of the big semicircle must be equal to pi r squared over 2. R is 5, so it is pi times 5 squared over 2, minus the area of the small semicircle, that is 3. And therefore, the area of the small semicircle is pi times 3 squared over 2. Here we took 2 as a common factor out of those two expressions, so the denominator will have 2. The denominator of this expression in total is 25 pi, while the denominator of this expression in total is 9 pi. So it is 25 pi minus 9 pi over 2. 25 pi minus 9 pi is 16 pi. So in total this expression equals to 16 pi over 2, that is 8 pi. So we shall find out that the area that we are looking for this question, that is the area of this green shape, is equal to either 8 pi square units in size, or in terms of numbers, the area of this green shape is equal to 25.13 square units in size. Okay, thank you very much.